Now we are going to look at the derivative as a function and explore in particular what can make a function fail to be differentiable. So if we go back to the definition of the derivative of a function at a given point, f prime of a is defined as the limit as x is approaching a of the difference quotient f of x minus f of a over x minus a, provided of course that this limit exists. This limit may fail to exist in the kind of ways that we have discussed for the existence of limits. In particular, one phenomenon that we have observed before that may lead to a limit that does not exist is if we have two different one-sided limits. Geometrically here, that would correspond to two half tangents, or what is often called a cusp. An example of a function for which we have this kind of situation is the absolute value function. So this is what the graph of the absolute value function looks like, and this is because when you take the absolute value of a positive number, you don't change it, and if you take the absolute value of a negative number, let's say negative 5, then you get 5. In other words, you take the opposite. So algebraically, that means that the absolute value of x is x if x is positive and negative x if x is negative. For the graph, that corresponds to two half lines of slope 1 and negative 1 respectively. So what can we say about the derivative of the absolute value function at 0? If we go by the definition in terms of the limit of the difference quotient, you see that we have a difference of definition of the function whether x is smaller than 0 or greater than 0. So we're going to look at the two one-sided limits at 0. The limit from the left, if x is less than 0, then absolute value of x can be replaced by negative x, and we obtain the limit at 0 of negative x over x, in other words, negative 1. That corresponds to the slope of the half tangent on the left-hand side, which is the left part of the graph. If we look at what happens from the right, then if x is greater than 0, absolute value of x can be replaced by x, and we obtain the limit of x over x, in other words 1. Since we have two different one-sided limits, the regular limit does not exist, and in particular, the derivative of the function at 0 does not exist, that is, f is not differentiable at 0. Another way we may have two half tangents is if we have a discontinuity, let's say something that looks like that. Then it is difficult to talk about the tangent to the graph at x equal a. So the picture suggests that continuity at a is a necessary condition for differentiability at a. And indeed, this is the case. In other words, if f is differentiable at a, then f is continuous at a. One rephrasing of that is that if f is not continuous at a, then it cannot be differentiable at a, because otherwise the function would be continuous. This is easy to prove because if we know that the derivative exists, in other words, the limit of the difference quotient f of x minus f of a over x minus a exists at a, then so does the limit at a of the same quantity multiplied by x minus a, because x minus a has a limit at a. Because both factors in the product have a limit, in that case we know that the limit of the product is the product of the limits. The limit of the first factor is f prime of a, because we assume that f is differentiable at a. The limit of the second factor is of course 0, and therefore we obtain f prime of a multiplied by 0, that is 0. But on the left hand side, what we have is the limit of f of x minus f of a, because we can cancel out the common factor x minus a at the top and at the bottom. So the limit of f of x minus f of a is 0. In other words, the limit of f of x at a is f of a, which is exactly the definition of the continuity of f at a. Another way a limit can fail to exist is if it goes to infinity. And an infinite limit, here f prime of a is the slope of the tangent line to the graph at x equal a. And so an infinite slope corresponds to a vertical tangent. Let's look at an example. For instance, the function cubic root of x, or x to the 1/3. This is what the graph looks like, and you see that at x equals 0, it looks like we have a vertical tangent. So f prime of 0 may not be defined because the limit may be infinite, but we can verify that. Indeed, the defining limit for the derivative at 0 would be x to the 1/3 over x, which rewrites as 1 over x to the 2/3. If x goes to 0, so does x to the 2/3, and therefore its reciprocal goes to infinity. So f is not differentiable at 0 because the defining limit does not exist. It does not exist because this limit is infinite, and that corresponds geometrically to this vertical tangent. Now for each x in the domain of f, we can look at f prime of x, the derivative, and the defining limit may or may not exist. But whenever it exists, to x we associate a new number, f prime of x. So this way, we define a new function that is derived from f, and we call it the derivative function of f. The first observation is that, of course, for f prime of x to be defined, we need at least f of x to be defined, so the domain of f prime is a subset of the domain of f. This might be a subset in the strict sense. In other words, it might be a smaller set than the domain of f. As we have already seen, for instance, the absolute value function is a function that is defined on the entire real line, but we have seen that its derivative is not defined at 0. It is defined, however, at every other value. For instance, if x is positive, then the tangent line to the graph of the function at that particular point is the line y equal x if x is positive. Therefore, it has slope 1. In other words, the derivative at x for positive x is 1. And similarly, the tangent line to a line is a line itself, so the tangent line to the graph of the function at a negative x is y equal negative x, and has therefore slope negative 1. But we have seen it's not differentiable at 0, so the domain of f prime is strictly smaller than the domain of f. Let's take a quick look at how the graph of the derivative relates to the graph of the original function. Here is a certain function f of x, and let's see what we can say about what the graph of f prime should look like. We're going to be rather rough here and just try to give an idea of how the two graphs relate without getting any very precise graph for f prime. The first thing we can look at are the horizontal tangents to the graph of f. If f has an horizontal tangent at a particular place, means the slope of the tangent is 0, and we know that the slope of the tangent is the derivative of the function at that particular x value. In other words, for the corresponding x values, the derivative is 0, so the graph of the derivative is going to cross the x-axis at these values. Now let's look at this part of the graph of f. And let's look at the tangent lines. Tangent line is negative, but as we get closer and closer to the horizontal tangent, the slope gets closer and closer to 0. In other words, the slope is increasing from a negative large value to negative values that are close to 0. Since the derivative takes at each point as a value the slope of the tangent line, we can interpret this graphically as a derivative function that takes negative value, in other words the graph lies below the x-axis, but is increasing. So we get something like that for the corresponding part of the graph of f prime. Of course, this is not very precise, this is just a qualitative observation. Now let's look at this following part of the graph of f. Now, the slope of the tangent line is always positive, the function is increasing, and the slope is increasing from 0 to a certain positive value. Then it's going to decrease again when we get out of the blue part, it's going to decrease again towards 0. So we get, for corresponding to the blue part, the slope of the tangent is increasing, and positive of course, and then as we go to this next part in the graph, the slope of the tangent is still positive, but now decreasing up to the point where it reaches the value 0 when we reach the next horizontal tangent on the graph of f. Now hopefully you get the picture, and following a similar type of reasoning, we would obtain this type of picture for the graph of f prime for x positive. A last remark before we turn to the next video. If y is f of x, we have various kinds of notations for the derivative of f. The one that we have introduced so far is f prime of x. Sometimes you will see df over dx, where here we emphasize the interpretation in terms of rate of change of f of x with respect to the variable x. In the same vein, it might be that we write dy over dx with the convention that y is really f of x. Sometimes you will also see capital df of x, but we will not use this notation much. Now you can move to the next video, and we will look at examples of calculations of derivatives.